All right, Chapter 2 lecture is about the structure and properties of organic molecules. Now in this chapter, I've omitted quite a bit of stuff that is in the book, but whatever I talk about in these videos is what you need to know. All right, wave properties of electrons. You've learned in your general chemistry class that electrons are not really particles, they're waves of energy. But they act as if they are a particle, they kind of act as like a standing wave, like they vibrate like on a guitar string. If you pluck it really slowly with low amount of energy, it has a very large kind of a vibration. If you pluck them really fast, then it'll have kind of more of a vibration, and if you pluck them really fast, then they'll have more. And all depending on the amount of energy, you can vibrate it faster or slower. So this is kind of the how it resembles a s orbital, which is kind of a sphere shape. Where imagine here is the plane, and it's going up and it's going down. If you pluck it faster, you get more of something like this, where you kind of have a p orbital, like how we have here, and you have a plane, a nodal plane in the center of it. Okay, so all depending on the energy that you put in, the electron is either going to vibrate faster or vibrate slower. Right, and the standing wave is actually all based on math. I don't believe they've actually seen these orbitals, or if they have, they're very hard to see. But it's based on mathematics. They describe the size, the shape, and the orientation of what they call a wave function, which is basically what we are calling the area in which you find the electrons. All right, and the amplitude, it could be a positive effect or a negative effect. Again, this is all mathematics. Pretty much what I want you to pretty much understand is that an s orbital is a sphere shape, and p orbitals have three. There are three types of p orbitals. There's a py, which the p is in the y-axis. There's a pz, where you can have this standing wave in the x-axis. I'm sorry, px, and then a pz is in 3 dimensions. It's coming in and out of the plane. So that would be a pz. Okay, and the node is basically where the amplitude is 0. Okay. So orbitals, what are these orbitals that we talk about? They are linear combinations of atomic orbitals, is basically what makes these bonds. So if you take these orbitals, an s orbital, p orbitals, and you combine them between two different atoms, you have a bond formation. Okay, so if you have like if you have an s orbital, actually, I'm sorry, you will see this in another slide, but if pretty much to explain it, if you have an s orbital, that's a sphere shape, and you have another s orbital, that's a sphere shape, and you add them together, you kind of get this overlap. All right, that overlap right there is what creates a bond. So combining orbitals between two different atoms, so if this is, let's say, one hydrogen atom, and this is another hydrogen atom, you get a bond formation. When you combine orbitals of the same atom, so if you have carbon and you combine the s orbitals with the p orbitals, you have what's called hybridization. Okay, and we will talk quite a bit about hybridization. But there are two types of bonds that covalent bonds can make. One is called a sigma bond, which is the strongest of the two bonds. Right, sigma bonds are the strongest between sigma, and there's something called a pi bond. This is the strongest, and what it basically is the electron density lies between the nuclei. Okay, again, we will see examples. A bond may be formed between two s orbitals, two p orbitals, sp orbitals, or hybridized orbitals of any of those combinations. The bonding molecular orbital is lower in energy than the original atomic orbitals. We're not really going to worry too much about this, but basically, if you have two atoms that want to bond, it's lower in energy for them to bond with each other than they are to be individual atoms. That's kind of the take-home point. So if you have two atomic orbitals, they are higher in energy than if they bond. Because when they bond, things start sharing electrons. Things become octet now. That's why atoms bond. That's why chemistry occurs, because nature always wants to be lower in energy. And this is the strongest type of overlap. Okay, so this is kind of an example. There's some fancy stuff in here I'm really not going to talk about, but really this is the one that I really want to talk about. This just kind of, sorry about that. This just kind of shows you you've got two orbitals, two s orbitals, and when they combine, when they start overlapping, they become this spherical one bonded orbital. All right, here's kind of another way of representing it. Okay, so the formation of and this is a sigma bond, opposed to a pi bond, which we will talk about, is a side-on overlap. This is more of a head-on overlap. When two 1s orbitals of two hydrogens overlap in phase, that's kind of what this is. We're not going to worry like too much about that. They interact constructively to form a bonding molecular orbital. All right, here is also a type of sigma bond where you have two p orbitals. All right, and when they meet, so if you remember in the first slide, they talked about that the electron densities were all in the same plane, or the nuclei. So it's basically saying here is the nuclei of one atom, here is the nuclei of the other atom, and all of the electrons are all in the same plane. That's what creates a sigma bond. Right? Pi bonds, really with two p orbitals, what a pi bond is, I'll show you here now, but we will talk about it in a different slide just to kind of show you the difference. A pi bond is, rather than these facing each other and having a head-on overlap, you have them parallel to each other, and you kind of get this overlap side-on. It's a side-on overlap. So you basically have this bonded to this. So if you notice, the electron densities in the nuclei are not in the same plane of each other. One plane is this way and the other plane is that way. You kind of have them parallel to each other. And that's what's called a pi bond. And we will see this in a different slide. I just want to show you the difference with p orbitals. So when two p orbitals overlap along the line between the nuclei, the bonding orbital, we're not going to worry about the anti-bonding orbitals, these little nodes here. We're not going to worry too much about that. Most electron density is in the middle, and the linear overlap is another type of a sigma bond. Okay. Here's just an example of a sigma bond with an s and a p orbital. So the first example we had, let me go back. This is an s and an s orbital. This is a p and a p orbital. Now we're going to mix an s and a p, and you basically just get an overlap here. And this is kind of what it looks like, but you can just imagine it just looking like this as well, with the sphere right there, and you have the overlap. That's kind of what this is trying to show you. Okay, don't worry about these anti-bonding stuff. It's a little bit more information that we need to have to talk about in this class. But overlapping, but basically a bond is between an overlap of an s orbital and a p orbital. Okay, like hydrochloric acid would be like something like this. Your hydrogen is in an s orbital, your chlorine, the valence electrons, is in a p orbital. So this is kind of the overlap of something like that. Okay, here's the anti-bonding. So notice here are my two p orbitals side on, and they kind of interact side by side. Again, do not worry about this up here. All right, this is anti-bonding stuff. We aren't really going to talk too much about that. But the pi bond is where you have side-on overlap. So a sideways overlap of two parallel p orbitals lead to a pi bond, molecular orbital, and again, we're not going to worry about that. The bond is not as strong as a sigma bond. Okay. Multiple bonds. Okay, let's talk about multiple bonds. This is when you start hybridizing things. And I'm going to ask you to watch the video on hybridization by the Khan Academy. I will talk about it in class too, but I want you to watch that video. These slides really don't have a good example of really explaining what hybridization is. So I want you to watch the video, and I'll also go over it again in class. But pretty much when you have multiple bonds, so this molecule would be something that has a double bond. It would be something like this. This is called ethene. All right, and notice I have a double bond in here. Okay, one of these bonds is a sigma bond, and the other bond is a pi bond. So this model right here is showing you here is the sigma bond. So you've got one orbital, it's going to be a hybridized orbital, and another hybridized orbital, and they're overlapping each other to give you a hybridized orbital. And then you have a p orbital here, and you have a p orbital on this carbon, and you kind of have this side-on overlap of that p orbital. So you have a hybridized orbital, that's head-on overlap, and then you have a pi bond. So the blue and the green are showing you the pi bond, and then the purple is showing you the sigma bond. Okay, so a double bond, two pairs of shared electrons consist of a sigma and a pi bond. Excuse me. And a triple bond are three bonds. A triple bond is three pairs of shared electrons, and it consists of a sigma and two pi bonds. So a triple bond, like acetylene, this would be acetylene, and here is my triple bond. All right, one of them is a sigma, and each of these is a pi, so I have two pi's. All right, and that looks something like this drawing is going to be horrific, but I just know even before I even draw it. But if it's bad, just look in the book. So that's my head-on overlap, my sigma bond, and then I'll have a p orbital in the y plane, which overlaps each other, and then I'll have another p orbital in the z plane coming in and out of the board, or the screen in this case, and with a side-on overlap. So each of those is a pi bond followed by the sigma bond in the middle. Shapes. Let's talk about the molecular shapes. These hybridized orbitals have particular shapes. The three shapes we're going to talk about is tetrahedral, trigonoplanar, and linear. Okay, so this molecule is sp3 hybridized. All right, and it has a tetrahedral shape with bond angles 109.5. Ethylene, these carbons are sp2 hybridized. All right, and you have a trigonal planar molecule, and the bond angles are roughly 120. And then finally, you have a linear molecule with 108 degrees. All right, the bond angles can't be explained with simple s and p orbitals. The only way to explain them is with hybridization and what was called VSEPR theory, valence shell electron pair repulsion theory, which basically says your molecules want to be as far away from each other as possible. So the easiest one is linear. So if I have a carbon, okay, and I have two atoms on either side, these are balls of electron. They have negative charged particles. So if I have two likely charged things, what's the maximum bond angle that they want to be in order to get as far away from each other as possible? Well, I want to be 180 degrees. That's why sp hybridized carbons are 180 degrees. All right. If I have three things, what do they want to be? They want to be as far away from each other as possible, and that would mean a trigonal planar molecule. Same thing for a tetrahedral molecule. Okay. So hybridized orbitals are lower in energy because the electron pairs are further apart. When they hybridize, they actually form these bond angles. So I'm going to quickly talk about what sp orbitals are, and then what sp2 orbitals are, and what sp3 orbitals are. But because I'm running out of time, we will do it in the next video.